Okay, so this is the second to last video on systems of linear equations before we move on to talking about matrix inverses after this. So this is something we've placed it in chapter 6 of the textbook. It could very well be in chapter 5. This is more or less going to be some theoretical considerations having to do with solving systems of equations, the different types of solutions that we run into. So rank is a quantity that is used to sort of classify different matrices, different types of systems. Um, so to keep things simple, we'll write everything in matrix form here. So if somebody gives me a general system of equations, right, we're gonna write down our matrix of coefficients here. We've got our vector containing our variables, and we've got our constants over here on the right hand side, right? So if we use these three matrices A, X, and B, then we know that this whole system here can be gathered up, and we can write it in matrix form as simply A times X equals B. We've seen this a few times now in these videos in class and in the text, right? Simply working out the definition of matrix multiplication gives us this form for a system. So any system of linear equations can really be viewed as a single matrix equation, right? Of course, if we want to actually go ahead and compute things, solve the system, we're going to have to work with the individual entries. But if we want to make some general statements about systems, it's nice to be able to make those statements about a nice sort of compact equation like this rather than writing out this whole system every single time. Okay, so we want to talk about the different types of solutions that we can have and what those solutions look like. So we know that when we want to solve a system, the first thing we do is we write down an augmented matrix, right? So what do we do when we write down an augmented matrix? We put our coefficients on the left, we put the constants on the right. We often put this vertical bar to separate the two. So we can write our augmented matrix as simply A slash B if we want to tell those apart, right? So now we can use that to talk about a general augmented matrix. And we know that the way you solve a system is you take this augmented matrix, you apply the Gaussian algorithm to it, so you apply some number of row operations, and you simplify that thing until you get down to row echelon form or reduced row echelon form. So we're going to assume that this guy here, this A prime slash B prime, okay, we'll assume that this is the reduced row echelon form for our system. Okay, and we've seen enough examples now that we know that there's really three possibilities that can happen, right? One is that we end up with this sort of situation here where everything on the left, to the left of this vertical bar, everything over here is all zeros, and we've got a 1 on the other side, or it doesn't necessarily have to be 1, but some non-zero number, right? If we actually are in reduced row echelon form, then of course, to be in reduced row echelon form, the first non-zero entry in a row should be a 1, so we might as well assume that it's a 1, right? Well, we know what this row tells us. This row says that 0x1 plus 0x2 down to 0xn. Well, that should equals 1. But we know that's impossible, right? Because this is just 0. 0 cannot equal 1, so there are no choices for the variables that are going to make 0 equal to 1. And so this is the case of no solution. Okay. Another possibility is that there is a leading 1 in every single column for A prime, for this guy over here on the left, right? So every one of the variables columns has a leading 1. We know that if every single variables column has a leading 1, we've seen that this is the case of a unique solution. Okay. And if we avoid cases 1 and 2, then it could be that not every we have a solution, right? So 1 is the case of an inconsistent system. 2 and 3 are both consistent systems, but 3 is a consistent system where not every variables column has a leading 1 in it, and we know that when this happens, we get infinitely many solutions, right? So we have infinitely many solutions. And we can say a little bit more. We know that every variable that doesn't get a leading 1 is going to be a free variable. So we know how many free variables we're going to have. If there are n variables in total, k of them come with leading 1s, then we have n minus k free variables. Okay? So n minus k free variables, or if we prefer, we can think of these as our parameters. All right. Okay, so one of the things that plays a major role in understanding what type of system we're dealing with, what type of solution we get, is the number of leading ones, right? The leading ones are going to tell us which variables are free, which variables are non-free, and so the number of leading ones is kind of a major indicator as to what type of solution we're dealing with here. So the rank is simply a way of counting the leading ones, right? This is sort of something we can do to quantify the leading ones and tell us something about the solution. So this is all the rank is. The rank is simply the number of leading ones in the row echelon form of A, right? We could say reducer echelon form, but we know that once we've got down to row echelon form, then we already know how many leading ones we have. I suppose I should not say the row echelon form, because there are many row echelon forms. There's only one reduced row echelon form. So we can use this notion of rank to more precisely restate the three cases that we saw on the previous slide. So the first one says, well, an inconsistent system is one where the rank of the coefficient matrix is less than the rank when you add on that row, or sorry, that column of constants, right? Because if we are in this situation here where we've got a row like this, right, where there's all zeros on the left, and then we've got this extra leading 1 sitting there in the constants column, right? That's one more leading 1 than we would have had without that last column, right? And so in this case here, right, we get that one extra leading 1. So this is saying that the rank of A slash B is 1 greater than the rank of A, because we get one more leading 1. Okay. Now, if the rank of A equals the rank of A slash B, then our system is consistent, and there are two cases that remain. So n here, n is the number of variables. Okay. So if the rank equals the number of variables, that's the case where we have a leading 1 in every one of the variables columns, and we know that that's our unique situation of a unique solution. The last possibility is that the rank is less than the number of variables, and that's when we have infinitely many solutions, and the number of free variables, the number of parameters, is given by the total number of variables minus the rank. Okay. One note to make here is that when you're trying to figure out, what possible values could the rank have, well, the rank is given by counting leading 1s, right? And every leading 1 occupies both a row and a column, and so that means that you can't have more leading 1s than you have rows, and you also can't have more leading 1s than you have columns. And so if I want to know what's the largest possible value I could have for the rank, I look at the number of rows, I look at the number of columns. Whichever of those two is smaller, that's the largest possible value for the rank. Okay. One of the things that tells us is that if we have more variables than equations, right, if n is greater than m, okay, then we know that the rank has to be less than or equal to m, which is strictly less than n. And so as long as our system is consistent, right, if we've got more variables than equations, then we know we have to have infinitely many solutions, right? It puts us in case 3. Okay, here are a couple of examples. Let's say we want to find the rank of our coefficient matrix, the rank of the augmented matrix, and then the solution of the system if there is one. Let's do the first one. So we'll do example 1. We'll put it down here. I think there might be room even. So let's go from here. Let me do the first row operation. So we're going to do row 2 plus 2 row 1. We're going to make that my new row 2. 1 minus 2 3 0 0 minus 4 7 4. We're doubling and then adding 0 minus 8 14 and 8. All right. Now the next step probably should be to multiply row 2 by minus 1 over 4, get that minus 4 into a 1, so we've got our second leading 1. But we can already see that row 3 is a multiple of row 2, so I'm going to do this. I'm going to do row 3 minus 2 row 2, make that my new row 3. 1 minus 2, 3, 0. That's going to give me row of zeros on the bottom. Next up, let me do a second step. I'm gonna do that other step. Minus 1 over 4 row 2. It's gonna become my new row 2, right? I want to make sure I keep those separate. So if I take row 2, I multiply by minus 1 over 4. I've got 0. I've got a 1. I've got minus 7 over 4, and I've got minus 1. Okay, so at this point, I can already tell you what the rank is, okay? I can tell you what the rank of A is. The rank of A is going to be 2. And notice that that's also the rank of the augmented matrix, right? Because there's no leading 1 sitting here. I've got a 0 there, so adding that 4th column does not create another leading 1, so those two have the same rank, and that means that my system is consistent, and then I could go ahead and solve. If I want to solve, I think we'd better get this all the way down to reduced row echelon form. It's going to be easier to read off the solution there, so I do one more step, right? We've done our forward steps. We've got this down to row echelon form. We've got one backward step to get to reduced row echelon form, which is I take row 1 plus 2 row 2. I make that my new row 1. 1, 0, 3, so 3 is 6 over 2. 6 over 2 minus 7 over 2 gives me minus 1/2. And minus 2. 0, 1, minus 7 over 4, minus 1, 0, 0, 0. Okay. So if we label these, let's say these are x, y, z. Let's say those are my variables. Well, now I can tell you what the solution is in this case. X is going to be equal to minus 2. So with this row, it says x minus 1/2 z equals minus 2. So we bring that over, I get a plus 1/2 z. X is minus 2 plus 1/2 z. Y is going to be equal to minus 1. So similarly here I will get minus 1 plus 7 over 4z. And z is free. And again, if you want to, you could always set z equal to t and write x, y, z all in terms of t.